Hey guys, welcome back to my course. It is one of those days again when um, I will be presenting asynchronously the content of this lecture. I apologize for that, and I'm looking forward to seeing everyone back on Wednesday. Okay, today we are beginning a new lecture and also a new topic, namely operational amplifiers. So far we've really dealt with mostly resistive circuits with some independent or dependent sources of voltage or current um, and a bunch of resistors. Now we introduce a new circuit component that is an active one, namely that it can supply energy to the circuit. So first of all, we will refer to these components as op amps. It stands for operational amplifier. It's a versatile element, meaning that it can compute a variety of transformations or operations on voltages. You can think of it as a voltage-controlled voltage source. So its inputs are 1 or 2 voltages, and its output is a voltage. It can also be used as a voltage or current controlled current source, but for the sake of this lecture, you should just think of it as a voltage controlled voltage source. So it's very much a dependent circuit element. And in this lecture, it will be demonstrated that an op amp can perform addition, amplification, integration, or differentiation. And so that's why we refer to it as an operational amplifier, because it can perform all of these mathematical operations. And so, I mean, essentially, circuit elements all perform math. And for example, digital circuits, like everything in your computer, comes down to either, at the lowest level, comes down to either an addition or a multiplication. And that's all done with binary digits, binary number representation. So here we're dealing with analog signals, meaning that the voltages that we will be summing, amplifying, integrating, or differentiating will be continuous voltages. And just if it's not clear, amplification really means multiplication, and it's generally by a number greater than 1. So whenever you need to boost your voltage to a higher level, you will use an amplifier such as an op amp. They're very inexpensive. They're something like pennies, maybe dollars a max per unit. And importantly, this lecture is kind of divided up into two phases, 2 stages. In the first stage, we will not make any assumptions about the input impedance of the op amp, and we will analyze it kind of without any underlying assumptions. And what we will see that is the math becomes very cumbersome, because we will have equations that will have very small numbers and very large numbers mixed in, and that just makes the math very unpleasant to handle. And so we will make use of what is called the ideal op amp assumption to allow us to more easily analyze the behavior of an op amp. And then we will introduce specific configurations of the op amp that allow you to invert a voltage, replicate a voltage, sum or subtract voltages. Okay. Again, an op amp performs mathematical operations on a set of inputs. So the inputs here are voltages, and there's 2 of them, although one of them can be grounded, in which case you can think of your op amp as having only one effective input. But there are 2 input voltages, and there's an output voltage. So another definition of an op amp is that it's an active circuit element It's designed to perform the operations of adding, subtracting, multiplying, dividing, differentiating, and integrating voltages. And so we will not cover what's inside the black box. So we will treat an operational amplifier as an input-output system, and we will learn how to define and solve for the relationship between the input and the output. We do not actually delve into how the op amp does what it does. What I can tell you is that it involves some elements that are really digital circuit elements. So we have transistors and diodes, which are nonlinear circuit elements, as well as resistors and capacitors. But again, for your sake and for for most practicing biomedical engineers, you do not need to understand how the op amp learns to add and multiply voltages, as long as you know how to design your circuit so that it implements the specific transformation that you want. And so they're typically available in these integrated circuit packages. So you probably have seen these dual inline packages or DIPs. So here is what one looks like. These will arrive to you in your circuit kit. You'll have a bunch of these, including an op amp. And so there are 8 pins. So a pin can either be an input pin or an output pin or power supply pin or unused, believe it or not. There's 8 pins and only 7 of them are used. I always found that pretty funny that in every op amp ever constructed, or every op amp of this configuration, one of the pins is just completely unused. And so the important pins are 2, 3, and 6. 4 and 5 are also important. Let me just maneuver my Zoom inset here. Okay, so pins 1 and 5 are not important. Pin number 8 is unused. So the other pins are the ones that we will focus on. The inverting input, that's pin number 2. In other words, or not in other words, rather, it will become clear throughout the course of this lecture why we call this the inverting input. For now, all I'm going to say is every voltage that gets connected to here will get appended with a minus sign. There's also the non-inverting input number 3. So any voltage here does not get inverted. So this is how, for example, if you want to subtract one voltage from another, you will apply the voltage that you're subtracting on number 2 and the voltage that you'll subtract from in number 3. The output voltage is on 6. So this is where you'll connect the wire where you want the result of the operation to sit on, number 6. And then you have a power supply. So you have a power supply, you have a positive lead and a negative lead, and those get put into pins number 4 and 7. So these will typically be, for example, plus and minus 9 volts. That's for an 18-volt source. And so here is the symbol for an op amp. It's this triangle with the minus sign that stands for the inverting input at the top, and the plus sign that stands for the non-inverting input at the bottom left. So these are your 2 inputs, and you have 1 output. We generally ignore the power supply when we analyze op amp circuits. However, you need to know that if you have, for example, a plus or minus 9 power supply, you will not be able to ask the op amp to output anything greater than 18 volts, for example. The power supply will dictate the maximum possible voltage that can be produced at the output. Okay, so as I've said, an input applied to the non-inverting input will appear with the same polarity as the output at the output. So it does not get inverted. Whereas anything that gets connected to the inverting terminal here will appear inverted at the output. And again, if this doesn't make sense at this point, don't worry. I think it will become abundantly clear as we go along. Okay, so here's another way of kind of drawing a schematic for what's happening in the op amp. And you have voltages that that lead to currents flowing into the op amp, and you have some output current here as well that you will connect your output lead to. And then your supply voltages get connected to inputs 4 and 7. So it is an active element, and it does require a power supply. And for example, if you think about this current that are flowing into and out of the op amp, they must obey KCL. Remember from the beginning of the course, KCL and KVL must always hold because they're fundamental laws that dictate the conservation of charge and energy. So for example, you can apply KCL at the op amp, right? So if you have I naught is the current flowing out, that's driving your output voltage, and you have the two inputs flowing in, I1 plus I2, plus the current from the power supply, I plus and I minus. So the sum of the 4 currents flowing in has to equal the total current flowing out of the op amp. So here is a much more useful picture. And this is the one that we will focus on for the rest of today's lecture. You have two inputs, V1 and V2, and they are connected across a huge resistance value. So Ri stands for input resistance, and its value is massive in the mega ohm range. And the voltage that forms across V1 and V2, we denote by VD, D for difference. And what you'll see is that op amps really amplify the difference between two voltages. And at the output node, you have this dependent voltage source. So A is, again, it's a huge positive constant. And VD is this voltage between V1 and V2. R naught is a series resistor that's connected to your dependent voltage source. Its value is very small, generally 50 ohms. So I don't know if you've ever bought BNC cables, for example, and they will be labeled generally with something like 50 ohms. And a BNC cable will often deliver a voltage from a device to another device, or to an oscilloscope, to a function generator, etc. And so this is your output resistance, which appears in series with this critical dependent voltage source. So remember, this is a voltage dependent voltage source. Why is it voltage dependent? Because the voltage that forms over here is equal to A, which is again a large positive number, times VD, which is the voltage difference between your two inputs. So what this system is doing is it's measuring the difference between your two inputs, and it's multiplying them with a large number and putting them across a small output resistance R0. And so Ri is the input impedance when looking from the input side. So if you're looking into this overall circuit from the left, all you're going to see is this large input resistance Ri. This is generally in the mega ohm range. On the other hand, if you're looking at it from the output side, all you will see is R naught. And so Ri becomes the input impedance, or the Thevenin equivalent resistance when looking from the inputs, and R naught becomes the Thevenin equivalent resistance seen from the output side. Okay, so an important quantity is the difference voltage, which is, again, the difference between V1 and V2. So that's what's going to get amplified in this next step. And so you can think of the op-amp as sensing the difference between its two inputs and multiplying it by a large gain A. And that large voltage appears at the output, again connected in series to that resistor R naught. And so the output voltage V naught of an op-amp is equal to A times V2 minus V1. And A is specified. A is like a property of the op-amp. So when you buy an op-amp, this A, this is called the open loop gain. Next, it will become clear in just a second why it's called the open loop gain, is a property of that op-amp. So you do not control it. You only control V1 and V2, and then the way that the output is connected to the input, which you'll see in a moment. Okay, so A is called the open loop voltage gain because it is the gain of our op-amp without any feedback from output to input. So notice that in this picture, there is no feedback between the output node and the input node. So this triangle here does not actually denote an electrical connection. It's just kind of, I actually find it confusing. So this triangle here is just there to try to illustrate that this is an op-amp whose circuit symbol is a triangle. But there's no actual connection between this point and this point, for example. And so it's very rare, by the way, to use an op-amp without feedback. You almost always have feedback in it. And so now some sample values for the open loop gain, the input, and the output resistance. So the open loop gain, again, is huge. It's millions to, what is that, tens of millions. The input resistance, again, it's astronomically high. It has to be very high for the op-amp to be able to produce that gain. The output resistance is small. A typical value is 50 ohms. And supply voltages, you're probably familiar if you've ever looked at the power supplies that power your electronic devices. They're generally in the order of 5 to 24 volts. And so now ideal value. So when we go on to make that ideal assumption, we will assume that the open loop gain will be infinite, the input resistance will be infinite, and the output resistance will be zero, right? And the reason that we'll be able to make that assumption is that the ratio of the input resistance to the output resistance is so huge that you can think of one as being infinitely larger than the other. Okay. So op-amps are almost always used with a feedback connection between the output node and the input nodes. And so negative feedback is the term that we use to describe the situation where the output is connected via a resistor to the inverting terminal of the op-amp. So here is a picture of an op-amp circuit. And so this is labeled 741. That's just a model of the op-amp. You don't have to memorize the actual the circuit part number or anything like that. What is important here is that this op-amp has two inputs. One of them is grounded, right? Notice that this positive input is grounded. And notice also that there is a connection between the output node here and the inverting input, and it's connected through a 20 kilo ohm resistor. Whereas there's also a battery, a voltage source, that's connected into the inverting terminal via a 10 kilo ohm resistor, right? So this is input node 1, this is input node 2. This is our input, V of S, and this is our output. And again, there's this feedback channel between the output and the input. And so the ratio of V naught to Vs is going to be called the closed loop gain. And gain is because that's what the op-amp is doing. It's taking some voltage and it's multiplying it by some scalar value that we call the gain. So if the gain is 2, your op amp will multiply your input by 2. And what we're going to see in this next, in the coming examples, is that the value of the closed loop gain is almost independent of the open loop gain. So whether the open loop gain is 10 to the 6th or 10 to the 7th, it has a very minor influence on the gain of the op amp when you employ feedback. But before we get into some examples, we do have to say a few words about saturation, which is an undesirable phenomenon. So as I mentioned, you cannot exceed, your op amp cannot be asked to produce a voltage larger than the power supply, because that would somehow mean the op amp will somehow supplying it, its own power. The power is obviously coming from the power supply. And so what it means is that beyond a certain point, the output voltage will saturate either at a large positive value or a large negative value. And so the x-axis here is the VD, which is the difference voltage. So it's the difference between V1 and V2. The output, the x-axis, sorry, the y-axis here is the output voltage, right? So the output voltage is linearly related to that difference voltage, and the slope of this line is equal to A in the open loop configuration. In the closed loop configuration, we have to solve for it, which we're going to do in just a second. But beyond a certain voltage, beyond a certain difference voltage, our op amp is simply not capable of reproducing the specified output. And what happens in that case is that the voltage clips. So VCC, for example, if you have a 24-volt source, the most that you can produce is minus 12 volts on the negative side and plus 12 volts on the positive side. And so the reason this is important is that you want to restrict yourself to working in the linear region where the output voltage is guaranteed to be bigger than negative VCC and smaller than positive VCC. Okay, so these are the three regions that your op amp circuit can be operating at. And you want to be in the middle region. You want to make sure that the result of the mathematical operation that you're asking your op amp to perform is restricted to this linear regime here. And so if we attempt to increase VD beyond this range, so if we put in a difference of voltages that is larger than this point on the x-axis or smaller than this point on the x-axis, then we will observe saturation, which means that the output voltage is really incorrect. So it's not equal to A times VD. It's going to be equal to VCC, even if AVD is bigger than VCC. Right? And so this is something that can happen in practice if you ask your op amp to produce a higher voltage than its power supply allows. And so in this lecture, we're just going to assume that we will be always operating in the linear region. But when you're designing circuits, such as in the lab or in general in practice, we must keep in mind that saturation can happen if we do not constrain our input to lying, in this middle section of the curve. Okay, so we come now to our first example. We are given a 741 op amp, which has the specifications given by an open loop gain of 2 times 10 to the 5th, an input resistance, of 2 mega ohms, and an output resistance of 50 ohms. and it's used in the following circuit. So again, the non-inverting input is grounded, so this is sitting at 0 volts. And the inverting input is connected to a battery in series with a 10 kilo ohm resistor. In addition, we have a feedback resistor between the output and the input and the inverting input. And so we are asked to solve for two quantities. Quantity 1 is the ratio of V naught to Vs. And quantity 2 is to determine the current I, which is the current along the feedback loop, when the source voltage here is equal to 2 volts. Okay, so in this circuit, we have to basically apply what we know about this circuit element, the op amp, and solve for the ratio of V naught to Vs. Okay, so this is a problem that I think when a lot of students see for the first time, they become very confused by. And so I'm going to do my best to unpack this and to go slowly and to make you see how to redraw this circuit, without this, because this triangle, we just don't know what to do with it. So we have to replace the triangle with what that circuit element is actually doing. But I'm happy on Wednesday to take some time at the outset of the lecture to answer your questions about this example. All right, so the first thing that we do is to redraw our picture. And so this is the leap from here to here is always, it can be difficult, right? So first of all, we like to draw our output on the right side, our input on the left side. So this here is input 2, right? Notice that input 2 is grounded. This here is input 1. So input 1 is the battery connected in series with a 10 kilo ohm resistor. Right? So we have this branch here corresponds to this branch here. And now we have to define the difference voltage between our two op-amp inputs, and we label that with VD. And we know that the resistor between them is 2 mega ohms. Why? Because we are told that the input resistance of this op-amp is 2 million ohms. And so this is input 1, this is input 2. Okay, so, and then at the output side, what the op-amp does is it multiplies this VD by the open loop gain, which is again given to us by 2 times 10 to the 5th. So I guess that's 200,000. So 200,000 times VD, it will be the voltage that will be produced in this spot where my cursor is. And then that voltage gets passed through to the output via the output resistance, which was given to us to be 50 ohms. Okay, so if there was no feedback, all we would have is this and this. But because we do have a feedback resistor from the output to the inverting input, we have to include it over here, right? And so this node here corresponds to this node here. And then this node here is the inverting input, which is over here. And between them is a 20 kilo ohm resistor. So again, the important things to note in this picture are the following. This is input 1, the inverting input. This is input 2, the non-inverting input. What the op-amp does, again, it acts like a voltage-dependent voltage source whose value is equal to the open loop gain times VD. VD is the difference between the two inputs. That voltage is connected through to the output, which is over here, via the output resistor, which here is given to us by 50 ohms. So now how do we solve for the ratio of V naught to Vs, right? And so remember, if unsure, always go back to first principles, which in the case of circuits is KCL and KVL. So what we're going to do is apply KCL, first of all, at node number 1. And so remember, we have one current flowing in, which is this current, and we have two currents flowing out. We have the feedback current, and we have this downward current. So let's apply Ohm's law. So we have Vs minus V1 divided by 10,000. That's the current from here to here. And then we have V1 divided by 2 million. That's this current, right? V1 minus 0 over Ri, which is V1 over 2 million ohms. And finally, we have V1 minus V0 over 20,000. That's this current. And so now you see that we're working with some very big numbers. Nevertheless, if you multiply both sides of the equation by 2 million, you observe the following equation. 200 Vs is equal to 301 V1 minus 100 V0. So we're interested in the ratio of V0 to Vs. And so what we're going to do at this point, we're going to make a simplification. We're just going to drop this one, and we're going to call this 300 V1. Right? We're going to just absorb that little numerical error. So we're going to say that this equation is 2Vs is equal to 3V1 minus V0. In other words, V1 is 2Vs plus V0 over 3. So we need a second equation. We need to somehow eliminate V1 from the picture, right? And the second equation we're going to get by applying KCL at the output node. So at node 0, we have one current flowing in, that's I, and we have one current flowing out. That's this current, the one flowing from right to left. So again, I, as before, is equal to V1 minus V0 over 20,000. That's over here. And this current here is equal to V0 minus AVD over 50. Remember, this node here is grounded, which means it's sitting at 0, which makes this node equal to A times VD, right? And so the Ohm's law applied to this resistor is V0 minus AVD over 50 gives us this current, which has to equal to this current, because there's only one current flowing in and one current flowing out. So again, we rearrange this equation and note that VD, which is specified here, is just V1, but with a negative sign, right? Because VD is defined as the positive end over here and negative end over here. So VD is equal to negative V1. So we can substitute negative V1 into here. And we also know that A is equal to 200,000. So we can substitute 200,000 into here. And then when you rearrange this equation, you can actually end up with another expression for V1, namely V1 minus V0 is equal to 400 times V0 plus 200,000 V1. So this gives us the second independent equation that we need to solve for the ratio of V0 to Vs. So now we have two equations that have V0, V1, and Vs. So we're going to be able to eliminate V1 as a variable. And the way we do that basically is if we rearrange for V1 in this equation and equate it to this, we end up with this result, which states that the ratio of V0 to Vs is approximately -2. And so the reason that this isn't exactly equal to -2 is because of this approximation that we made in the coefficient on V1. So if we would have kept the 301 V1 in this equation, we would have arrived at a ratio of V0 to Vs of exactly -2. In any case, you can see that this discrepancy is tiny, and it's clear that the ratio of the output voltage to the input voltage is approximately equal to -2. In other words, this circuit is taking the input voltage Vs, multiplying it by 2, and then inverting it. So for example, if Vs was equal to 5 volts, the output will be equal to -10. So the other thing that we are asked to solve for, I believe, is the value of the current I here. And so I will just demonstrate now how to solve for I. So we had a few expressions here that had that current I represented with Ohm's law. And so notice that the current I is going to be equal to V1 minus V naught over 20K. So we somehow need to figure out what V1 is. But we can get that from, for example, from this equation. Right? So, and we were told to solve for current I when Vs was equal to 2 volts. So if we apply 2 volts into Vs, negative 4 volts for V naught, then we get that V1 has a value of exactly 0. Right? So this node becomes grounded as well, which is interesting. You should think about that, what that means in this picture. Right? So again, if you stick in Vs as 2 volts, and if you apply V naught is equal to negative 4 volts, which is exactly what our amplifier dictates, then we arrive at a value of 0 for V1. So now it's straightforward to calculate this output current I. We simply apply Ohm's law, so 0 minus V naught divided by 20,000 ohms gives us an output current of 200 microamps or 0.2 milliamps. So it's a very small current, which is generally the case with op amps. So I know that some of you are probably confused. I mean, mostly by the transformation between the circuit that we were given, where the op amp symbol was just denoted with a triangle, and this picture that we drew. So we're going to do one more example that hopefully will help you understand exactly how we went from the op amp, the triangle, into this picture. Again, the main thing is that you have a difference voltage at the input that's multiplied at the output side by a value who's specified. So remember, Ri is a property of the op amp, A is a property of the op amp. We control the inputs and the feedback resistance. And depending on the inputs and the feedback resistance, V naught will take the resulting value. All right, another example. So this is the same op amp as before. So when you see this, what that means is that the open loop gain is still 200,000. And let me just recall what the input impedance was. So the open loop gain was 200,000 and the input resistance was 2 million. Output resistance was 50 ohms. So those same three specifications hold for this example. Now the difference here is in the way that the resistors are connected. So first of all, we have an input that's going directly into the inverting input. So we have a battery V of S that's connected to the inverting input. And on the output side, on the non-inverting input side, we have feedback. So we have a 40 kilo ohm resistor that is connected directly from the output into the non-inverting input. And we also have an alternative feedback loop, which is the outside here. So this output current here can either take this path or it can take the outside path. And so we have to be able to draw the schematic corresponding to this picture while observing the input-output characteristics of the op-amp and having these resistors connected at the right nodes. So here's the picture that we're starting from. And now I'm going to do my best to show you how we transform this into a circuit diagram that we can apply KCL and KVL to. All right, so again, this tends to cause confusion, so I'm going to try to walk through it slowly. So the inverting input, the minus sign here, corresponds to this node here, node number 1. And so notice that our source voltage is, or sorry, I already made a mistake here. The input voltage is the inverting input is actually up here, and the non-inverting input is over here. So this node 1, the node that's labeled 1 in this circuit, corresponds to this node here. And this node corresponds to the inverting input pin of the op-amp. So notice that our battery, our input voltage, is connected directly directly to the amplifier's inverting input, which means that there is this large input impedance between Vs and the non-inverting input of the amplifier, right? So this here is the input side of our op-amp, right? So this, what I'm highlighting with my cursor here, corresponds to this section of the circuit. We also have a resistor of 5 kilo ohms between the non-inverting input and ground. So always assume that the bottom is ground. So this all here is grounded. Right? So we have a 5 kilo ohm resistor between the positive input and ground. And now we also have a 40 kilo ohm resistor here between the positive input and the output. Right? This node here is the output of the op-amp. It's even labeled as such in the question. So the output node is over here, number 2. So number 1 is the positive input, and number 2 is the output. Okay, so we also need to represent this 20 kilo ohm resistor between the output and ground, right? This is the output and this is ground. And now I guess the tricky part here is that we know that the output voltage of the op-amp has to equal to AVD connected in series with a 50 ohm resistor, right? So the tricky part here is really understanding why it is that this is drawn over here. So what this portion of the circuit dictates is that the voltage at node 2 has to equal to the difference between the two inputs of the op-amp, so the voltage across the 2 milliohm resistor, multiplied by A and connected through a 50 ohm resistor, right? So this section just guarantees that the output voltage, the output node of our op-amp abides by that equation for the output voltage of an op-amp. So the way I've drawn it this way so that you can see the sections of the op-amp. So this section obviously is equal to this section. And then, you know, I could have drawn the battery up here, but I drew it down here because I wanted to indicate conveniently that the negative pole of the battery is grounded of this dependent voltage source. Okay, so again, I'm happy if you guys want to ask me on a Wednesday to go over this step by step, I'm happy to do that. So again, we've mapped our op-amp circuit with this 40 kilo ohm feedback resistor between the output and the positive input into this circuit diagram. And what we need to do now is to write the KCL equations for node number 1 and node number 2. So let's start with node number 1. Again, the current direction arrows have been labeled. So we have one current flowing in and two currents flowing out. So the value of this current is equal to Vs minus V1 over 2 million ohms. The value of this current, the value of this downward current is V1 divided by 5,000 ohms. And the value of this current flowing from 1 to 2 here is V1 minus V0 over 40,000. So remember that node 2 is sitting at V0 because node 2 is the output of the op-amp. So that's our first equation. Now our second, before we do that, let's rearrange this. So again, there's some unpleasant manipulation here. And all I'm going to do is I'm going to write this as an equation with V1 multiplied by a scalar minus V0, again, divided by 40,000 is equal to Vs over 2 million. And so you can think of this as an equation of V1, V0, and Vs. And the rest are just the coefficients. So now let's apply KCL at node number 2. Again, we have two currents flowing in. That's this current and this current. And we have one current flowing out. That's this current. So as before, the left to right current flowing in is equal to V1 minus V0 over 40,000. And this current here is equal to AVD minus V0 over 50, right? Because this point is sitting at 0, this point is sitting at AVD, and this point is sitting at V0. And finally, the downward current over here is equal to V0 over 23 or 20,000. So we can again make those substitutions that are given to us in the specifications of the 741 op-amp. So we have an open loop gain of 200,000. And by definition, VD is the difference voltage between the non-inverting input and the inverting input. So V1 minus Vs, right? Because this point here is sitting at Vs. Right? So V1 minus Vs is equal to the difference voltage. And so now we can substitute these into here. And we arrive at another equation that has V1, V0, and Vs. And we can simplify that again. So we have another equation that has V1 multiplied by a constant minus V0 multiplied by a constant is equal to Vs multiplied by 200,000 divided by 50. Right? And we can put that all now into a 2x2 system of equations, right? And the only tricky part here is that we have Vs on the right-hand side of this equation and this equation. So we Vs, because it applies to the equation 1 and equation 2, is a multiplier of the right-hand side equation. If you want to work, if you're not comfortable with the matrix notation, you can just use substitution and solve for the ratio between V0 and Vs. But it's convenient here to specify this 2x2 matrix. So these are our coefficients on V1, Vs, V1, V0, V0, V1, V0. So equation 1 is this coefficient times V1 plus this coefficient times V0 is equal to 1 over 2 million times Vs. The second equation is this coefficient multiplied by V1 plus this coefficient multiplied by V0 is equal to 200,000 divided by 50 VS. And so if you recall from linear algebra, hopefully you're all somewhat familiar with a matrix inverse. One way of solving for V1 and V0, actually the first thing we do is we divide both sides of this equation by VS. And what that does is it turns our variables into ratios. Right? So if you divide V1 by VS and V0 by VS, you get those ratios appearing as a variable. And the second thing that we've done here is we've multiplied both left and right hand side by the inverse of this 2 by 2 matrix. So this is the inverse of a 2 by 2 matrix is just another 2 by 2 matrix. And if you actually plug this into MATLAB or your programmable calculator, you'll see that the ratio of V0 to VS is approximately equal to 9. So it's 9 and where is that? 4 over 10,000 or something. The other thing that we get from this is we have the ratio of V1 to VS, which is approximately equal to 1. So in this circuit, V1 and VS are equal to each other. So think about what that means, right? We have VS here and V1 here, and they're about equal. So what that means is that there cannot be much of a voltage drop across this large resistor. So that will really come into play when we study the ideal op-amp assumption. And now finally, we also have been asked to solve for the output current I0. Right? I0 is the current coming out of the op-amp into the 40 kilo ohm resistor, which in our circuit is this current here. Right? So again, we can just apply Ohm's law and AVD minus V0 divided by 50. If we plug in all of our numbers and solve, we arrive at a value of 0.065 milliamperes, or I guess that's 65 microamps. So again, a very small value, which is customary with op amps. Okay, just a note, if this algebra, the linear algebra here confused you, again, the only thing you need to understand is that you have two equations, and even though it looks like you have three unknowns, because you're asked to solve for the ratio of V0 to Vs, you actually have two unknowns, and you can solve for those unknowns however you want. Okay, so again, historically, the first part of the op-amp lecture, the part that we just covered, gives people fits, and it confuses people and it scares people. So don't worry, because the rest of the op-amp lecture is much more accessible. And we're going to basically assume going forward that our open loop gain is infinite, our input resistance is infinite, and we have no output resistance. And what you will see is that it will make our life a lot easier. It will kind of eliminate the occurrence of these very large and very small numbers in the same equation. And it will just make solving for the op-amp gain a lot easier. For example, in this case, the gain would have been 9 and like exactly equal to 9. And in this picture, in this op-amp here, the gain would have been equal to -2. And so we do not need to actually explicitly write out or explicitly draw the input terminals and the output terminals. Fortunately, by making these ideal op-amp assumptions, we can make our calculations a lot simpler. And that is what I want to begin with you guys on Wednesday. I hope that you got something out of this lecture, and I look forward to seeing everybody back in class on Wednesday.